Spanning sets. Determine whether the set S spans R2. If the set does not span R2, then give a geometric description of the subspace that it does span. So here we have this set consisting of the single vector, -3, 5. So if this set S spans R2, then that means we can create other vectors from this vector. So let's say that we'll take a constant C sub 1 times this vector, -3, 5, and we'll pick a vector, for example, 1, 1. So what this means is that if we multiply C sub 1 by -3, giving -3 C sub 1, we'll get 1. And if we multiply C sub 1 times 5, we'll get 5 C sub 1 equal to 1. So solving the first equation gives C sub 1 equal to -1/3. Solving the second equation for C sub 1 gives 1/5. We can see that we can't have two answers. So this tells us that this is not possible. So this means that S does not span R2. We can't have two different solutions for C sub 1. And we'll note that we should have two vectors spanning the space in order for this to be possible. What we'll have to do is we'll then take a look at a geometric description of the subspace. So let's suppose we were to look at, let's say, a two-dimensional plane where we have x as the first coordinate and y as the second coordinate. Well, if x is -3, that means that y will be equal to 5. We'll get a point over here. And then if we look at multiples of this, so we can have any multiples of this. So 1 times this vector just gives the vector, -3, 5. If we look at, let's say, 2 times that vector, we get 2 times -3, 5, giving us -6, 10, which will be somewhere over here. And then if we were to look at -1 times the vector, we would get 3, -5, which would be somewhere down here. And then -2 times the vector, that would give us 6, -10, which would give us something somewhere around here. We can see that what would happen is if we were to plot more points corresponding to multiples of this vector, we would wind up just getting a straight line. Of course, this is just a rough sketch of a straight line. So we would get a straight line passing through these points. And so in this case, to answer the question, to give a geometric description of the subspace that this set does span, it's going to span a straight line. Spanning sets. Determine whether the set S spans R2. If the set does not span R2, then give a geometric description of the subspace that it does span. So we have this set S consisting of the vectors 1, 3, -2, -6, and 4, 12. Well, one thing that we can note right away is that if this does span R2, we'll be able to create other vectors from this set. But if we notice the first vector, 1, 3, if we multiply that by -2, we get the vector containing -2 and -6, which is the second vector. If we multiply that same vector 1, 3 by 4, we're going to get 4, 12, which is the third vector. So the second and third vectors, these are not linearly independent of the vector 1, 3. So really we only have one vector. So we can consider just the first vector, 1, 3. And so if this were to span R2, then we would be able to take a constant, let's say C sub 1, and multiply it by the vector 1, 3, and get any other vector in R2, for example, 1, 1. So if that were the case, then we'd multiply C sub 1 times 1 to get C sub 1 equal to 1, the first term here. And then if we multiply C sub 1 times 3, we'll get 3 times C sub 1 also equal to 1, meaning that C sub 1 is equal to 1/3. But C sub 1 cannot be equal to both 1 and 1/3 at the same time, so this is not going to be possible. which tells us that the set S does not span R2. So then we just want to see if we can give a geometric description of what the subspace that it does span is. So what we can do is we can take a look at what the vector would look like, or what this subspace would look like in a two-dimensional plane. So we'll look at this for a few different points. So what we'll do is we'll note that for the first vector, 1, 3, we'll let x be the first coordinate and y be the second coordinate. We'll get 1, 3. And then if we were to multiply that vector by -1, we would get -1, -3, which would be down here. If we multiply it by 0, of course, we just get 0, 0, the origin. And if we were to multiply, let's say, by 2, we would get 2, 6, where 6 would be up here. So we would get 2, 6. And we can see that those points are all going to lie along a line, showing us that the geometric description of the subspace that this set does span, well, that's going to be a straight line. Spanning sets. Determine whether the set S spans R3. If the set does not span R3, then give a geometric description of the subspace that it does span. So we have this set S consisting of the vectors -2, 5, 0, and 4, 6, 3. So if this set spans R3, then we should be able to create any vector in R3 from these two vectors. So we could choose a vector, we'll call it U, equal to 2, 1, 0. And what we'll see is if we can find some linear combination of these two vectors to form U. So we'll take a constant c sub 1 times the first vector, -2, 5, 0, and then we'll add a constant c sub 2 times the second vector, 4, 6, 3, and we'll want that equal to the vector 2, 1, 0. Well, from this equation, we'll see that we can multiply c sub 1 by -2 and c sub 2 times 4, giving us -2 c sub 1 plus 4 c sub 2, and that will be equal to 2. And then when we multiply c sub 1 by 5, we'll get 5 c sub 1, and c sub 2 times 6, we'll get 6 c sub 2, and that will be equal to 1. And then finally, we'll have c sub 1 times 0, which will be 0 c sub 1, plus c sub 2 times 3, or 3c sub 2, and that will be equal to 0. So from the last equation, we can see that if 3 times c sub 2 is equal to 0, that means that c sub 2 will be equal to 0. And if we plug that into the first and second equations, what will happen is we'll simply get -2 c sub 1 equal to 2, and 5c sub 1 equal to 1. So from the first equation, we'll see that c sub 1 is equal to -1, and from the second, c sub 1 is equal to 1/5. But c sub 1 cannot take on two different values, so this is not possible, which tells us that S does not span R3. So we saw that we could find a vector in R3 that cannot be created from a linear combination of these two vectors in S. So that tells us that S does not span R3, but then we would like to have a geometric description of the subspace that it does span. Well, if we look at this, we see that we have two vectors. So if we have two vectors, we can't span all of R3, but we can span a two-dimensional space, which means that we're going to span a plane. So the subspace that this set does span is going to be a plane, a two-dimensional surface. Spanning sets. Determine whether the set S spans R3. If the set does not span R3, and give a geometric description of the subspace that it does span. So we have the set S consisting of the vectors 1, comma, negative 2, comma, 0, and then 0, comma, 0, comma, 1, and finally negative 1, comma, 2, comma, 0. So if this set does in fact span R3, then that means that we should be able to take some linear combination of the three vectors. So we can take a constant c sub 1 times the first vector, 1, comma, negative 2, comma, 0, plus the constant c sub 2 times the second vector, 0, comma, 0, comma, 1, plus a constant c sub 3 times the third vector, negative 1, comma, 2, comma, 0, and that will be equal to some vector which we'll call u, consisting of u sub 1, comma, u sub 2, comma, u sub 3. So we'll be able to find some linear combination of these vectors that will make this work. Now, one thing we can note right away is that the first vector and the third vector, when we look at this, these are just multiples of each other. If we take negative 1 times the first vector, we get negative 1, comma, 2, comma, 0, which is the third vector. So this tells us that c sub 3, that will simply be equal to 0. So because that vector can be created from the first two. So we essentially just want to know if these first two vectors will span this space. So we could consider just a specific vector. So let's suppose we take a combination c sub 1 times 1, comma, negative 2, comma, 0, plus c sub 2 times 0, comma, 0, comma, 1. And we'll take this specific vector, u sub 1, u sub 2, and u sub 3. So we'll see if these are equal to each other. So this will give us a system of equations. We'll have c sub 1 times the 1 and c sub 2 times the 0, so just c sub 1 plus 0 c sub 2, and that will be equal to u sub 1. And then we'll have c sub 1 times negative 2, so negative 2 times c sub 1, plus again 0 times c sub 2, and that will be equal to u sub 2. And then we'll have, for example, the third one, c sub 1 times 0, so 0 c sub 1 plus c sub 2 times 1, or c sub 2, and that will be equal to u sub 3. So when we solve the first equation for c sub 1, we can see that here we have 0 c sub 2. We'll find that c sub 1 is equal to u sub 1. And then for the second equation, we also have 0 c sub 2. So if we can divide both sides by negative 2, we'll find that c sub 1 will be equal to negative u sub 2 over 2. And from the third equation, we'll see that c sub 2 will be equal to u sub 3. But the problem here is where we have two possible solutions for c sub 1, telling us that this is not possible. We can't have two values for c sub 1. So this tells us that S does not span R3. So we wind up getting something that's impossible. So S does not span R3, but as far as a geometric description, well, we see that we only have two linearly independent vectors. This third vector is a multiple of the first, but the first and second, they are not multiples of each other. So if we have two linearly independent vectors, then the subspace that they will span will be a plane. So we'll span a two-dimensional surface. They're going to span a plane.